All right, so my name's Dean. I work for Cash App, and we'll talk a little bit about our journey training large language models for customer support. So customer support at Cash App looks a little bit like what I have on the screen here. I took a video on my phone on the left here. I'll play that. So this is me using the app. I can click in the upper right and view my profile, and then scroll down, click support. And once this loads, a bunch of support categories are going to show up, like how to add money or savings accounts or investing. So you can click at the bottom on chat and you can type a message here. And this will send your message into the backend system. So I'm going to type something like, I need to reset my PIN number, and then not send that. But if I did send that, it would go into this next system with the robot emoji above it. This is a system my team runs called CashBot. It uses a lot of kind of traditional NLP, deep learning, things like that to analyze conversations, look at messages that our customers are sending, understands like if there's actions we can take. So if someone sent the message, I need to reset my PIN, our models will kind of identify that. There's a rule engine that sits on top of it that I'll talk a little bit later, and then we'll take action. So here we'll send them an in-app flow that allows them to kind of solve that problem on their own. That system handles a number of different customer issues, but inevitably there are issues it doesn't handle. And so if we can't handle it, we'll pass it over to this other system on the right here, with the kind of headset emoji above it. This is our human support reps that are kind of working in the back end, looking at customer conversations and taking actions themselves. We run ML systems in this also. So maybe you can see here, there's like some little annotations in this drop down here that'll say suggested. So if a customer writes in saying like, I need to access my accounts, but I can't, can you help me? We'll give them kind of suggestions. And these things they'll populate that free text field below with some template text. So I'll talk a little bit about that later too. These are both largely kind of extant NLP systems, and we have many, many other use cases like this. And so I'm going to talk a little bit about how we can think about incorporating LLMs into both of these. The one on the left I think is pretty straightforward. We're sending text back to the customer, so generating text there is a pretty typical use case for LLMs. This other one on the right, where we're doing things like classifying things, is maybe a little bit more interesting to think about. I'll talk about that one too. So moving on, customer support is what I'll call a closed domain. And so what do I mean by that? Typical LLMs, if you take one off the shelf, like OpenAI's GPT family, or Llama from Meta, are open domain assistants. They're knowledgeable about any topic that came up in its training data, and they can be instructed to perform many tasks, like writing Python code, summarizing meeting notes, writing an email, so on. Customer support is a closed domain, and there are many other closed domains out there. For customer support, so if you're an assistant, whether you're a human or a virtual assistant like an LLM, you really only need knowledge about this domain. So for us, that's knowledge about Cash App. Maybe you need a little bit of knowledge about general consumer finance, like what a checking account is and how that differs from a credit card or something like that. And if you're an assistant in this domain, you should only perform tasks related to customer support. So you shouldn't be able to generate Python code. If a user writes into customer support and asks this, even of a human, we should send back text saying, we can't do that. We help you out with Cash App. And so closed domains allow specialization. So if people saw Apple's announcement yesterday, they're running some small models of the size that I'll talk about here, where they train like specialist models for each specific task. And this affords them the ability to have very direct control over model size, very direct control over model latency. Also, I think models are less likely to be jailbroken to perform arbitrary tasks. This is a little bit of a running hypothesis in our group, but if we have very tight control over models and we train them to do very specific tasks, it's less likely they're going to do things like generate arbitrary code or be instructed to write meeting notes or something like that. And then finally, if you run your own specialized models in-house, you're naturally going to improve privacy. For some use cases like ours, you might even need to access customer data. So for us, we might need to look at, say, customer transactions, maybe a list of them, and those can be identifying, right? If I know you made 5 transactions at certain merchants, I can probably start to have an idea of maybe where you live if those merchants are in a certain city or something like that. And so customer support oftentimes involves looking at those things, and so we might necessarily need to run private models where we're able to use that information. So prior art and closed domains, I'll just go over kind of some other examples to give people an idea of things outside customer support. A couple years ago, there was something called Biomed LM. That was around 3 billion parameters, and the way it was trained was there's a very large data set called the pile. It's open domain web text, but they filtered it down to around 30 billion tokens, just biomedical abstracts and literature. And there's some performance over on the upper right of this slide. You can see that Biomed LLMs bolded. It beat out a number of models underneath it, kind of at the time. These days, it's been bested by few-shotting GPT, or sorry, zero-shotting even GPT-4, but there are still trade-offs there, right? Like GPT-4 is still quite slow, maybe compared to a 3 billion parameter model. Another good example of this is ChipNemo. This comes from NVIDIA's research groups. It comes in 7 billion and 13 billion parameter variants. It's because it's trained off of Llama 2, and so those are Llama 2 model shapes. So, but they took around the same number, around 23 billion tokens of chip design docs and code. This is all kind of proprietary and internal to NVIDIA. And then they also formed a smaller data set of instructions to tune this model for instructions around chip design. But if you look at the bottom right there, the red and green bars, which are the ChipNemo models, they compare them to kind of the original Llama variants. And depending on the exact task, like chip design or scripting, chip design languages, they do quite a bit better than the off-the-shelf variants. And then finally, maybe if anyone's used like a coding LLM here, I think you can think of these as a closed domain model. They're only ever generating like code syntax in your IDE. They're not doing kind of other types of things that you might expect like a more general open assistant to do. Code Llama specifically comes in, again, Llama shapes here. Depending on the size of the model, they train on quite a bit more data than the other examples, 500 billion to 1 trillion tokens. So moving on to what we do here. So I'll talk about how we do our pre-training. So we're gonna start with the simplest pre-training we can. Our data looks a little bit like this at the right, where we have a very, very large number of customer support transcripts. So maybe and these are all diarized, so we have kind of 3 participants in our conversation. A customer who writes in says something like, what's the balance on my account? We have a system. This is kind of heuristic based. I think this one, must have written in and gotten queued. So the system says, we'll get you to someone who can help. You don't have to wait, we'll notify you. And then the customer responds back. Eventually, I just put some ellipses there. Our support reps, we call them advocates because they advocate on behalf of the customer. They solve the customer's problem, but we've got tens to hundreds of billions of tokens of these types of transcripts. And so that's what we're gonna use for our pre-training. One thing I'll point out is hallucinations are very, very possible. And I'll point this out on a subsequent slide, but if you ever talk to customer support, even outside of Cash App, one very common thing to do is like pull up the customer's account just to kind of get a better idea of what problems they might be having. And so oftentimes that's hidden information. It doesn't show up in these transcripts, but a customer service rep might use that information to solve a problem, and they might talk about what they find there. So that'll be a very prime source of hallucination, and I'll talk about how we deal with that. There's many typical tools for this. Kind of at the cornerstone of all of them is Hugging Face transformers. I'm sure many people in here are familiar with that. But layered on top of that, you have kind of model sharding technology like Microsoft's DeepSpeed, or built into PyTorch, they have something called fully sharded data parallelism that allows you to take like a very large model and distribute it across multiple devices. You have more specialized toolkits, like NVIDIA has one called Megatron LM. And then there's also third-party APIs emerging where you can just take your data, upload them to some web service, and it will fine-tune a model for you. The primary differentiator across all these is maybe how much data you can send. So if you're using a third-party service, they might have limits on how much data you can upload, and really just how fast they go. They're all performing this very simple objective function that's the kind of language modeling objective function at the lower right, where given any token x sub I, you're gonna look at all preceding tokens x sub 1 through x sub I minus 1, and just try to kind of maximize that probability. And the primary differentiator is just how quickly they can do that operation. So NVIDIA Megatron, for example, has many, many optimizations built in, is very efficient for doing this one thing, and other toolkits maybe aren't as fast, but they can fundamentally do that same operation. So here's some examples of once we pre-train our models, what they can generate. They essentially generate entire support transcripts. So I've bolded here what I've given as input to the model. So here I say I'm a customer and I want to know the balances on my accounts. And I put the system prompt in there too. If I didn't, this would typically generate something like that. But you can see here that we have policy on how you would get the balance of your account. So if you kind of read through this at your own pace, near the bottom, the customer support advocate says to view your balance, sign into your app. And then if you click on the money tab at the bottom left, you'll see your balance right there. So based on training on all of these transcripts, as long as we do a good job at curating our data to kind of what our current policy is, we'll essentially learn knowledge of what customer support on Cash App looks like. The data is very self-consistent. So here's another example. We've changed how we do this over time, but it's not uncommon for us to ask customers for feedback during a support session to understand how we're doing. And so if I'm prompting this model and say, oh, you didn't help me, I'm really frustrated now, and then I ask, a system would typically give this request for feedback. And in the past, we've used kind of a 5 emoji Likert scale. So the frustrated face is the worst results you can get, and the face with hard eyes is the best. And there's kind of 3 other grades in between there. But if you are a customer and you say you're frustrated and you're mad, and then ask for an interaction rating, then the model will generate kind of the low score. If you're a customer and say, oh, that solved everything, and then ask for the rating, you'll get kind of the highest score. So they're very self-consistent, kind of like you'd imagine. And here's kind of the hallucination example I was alluding to before. So if I'm a customer and I say, what is this $9.99 transaction every month? I don't want that happening. And then play out the conversation. You'll see here in pink, I've got what we think an advocate might say there, is that it's a $9.99 payment from Google YouTube Music. And so again, this is very indicative of what happens in our domain, and what I really think happens in most customer support domains is like a customer support rep might go pull up the account, go look at some recent transactions, and try to infer what it is the customer is having problems with, even if they didn't mention it. So here they did mention, it was $9.99, but I'm not even quite sure if Google YouTube Music is a thing. I think you can get a YouTube Music subscription. I don't know if it costs $9.99, but this is just, kind of generated based on, reasonable information in the pre-training data set. And so I'll talk a little bit about how we're gonna solve that problem later. When you train these models, this is kind of your typical training curves. I'm just showing train loss here. This is what's typically done in kind of the model scaling and pre-training literature, mainly because once you have tens or hundreds of billions of tokens, the notion of kind of an epoch through your data where you typically look at your evaluation loss makes less sense and is kind of expensive to run. So we do run evaluation throughout this. We don't see any signs of overfitting, but I think the training loss is more illustrative for what I want to talk about. So kind of the first thing to note here is that you get these typical model scaling effects. So the smaller the model, kind of the worse it does. And here we might get diminishing returns. You can kind of look at the relative drops of loss in between these model sizes. And so it's going to become very important for us to quantify like how much is 0.01 difference in train loss worth. Loss drops relatively rapidly. This is true for if you're training from scratch, or if you're taking an off-the-shelf model and adapting it, maybe over the first 5 billion tokens or so. And then after that, you kind of enter a linear regime where loss just kind of drops linearly. I ran this out, I think, for it looks like 25 billion tokens. It flattens out at the end for me, because this is when like my learning rate scheduler kind of decreases towards 0. But many of these models will just kind of continue learning if you continue feeding them data. This was pointed out kind of in the original Llama papers, and why kind of Llama 3, they're now training with many, 15 trillion tokens, I think, for the model sizes that they trained in the first paper. They found that the loss basically keeps on going down. I think we'll probably hit a floor here because our loss is quite low compared to the loss numbers you'd see in kind of an open domain. But there is kind of the promise that you can just put more data into these models and they'll kind of continue to soak it up in their knowledge. Spikes are pretty normal in these loss curves. This is just kind of a fact of life when training large language models. We know what they're caused from a little bit. Model size, the larger the model, the more likely you are to get a loss spike. So you'll see the green curve has several spikes. There's a large one right before 4 billion tokens, but we do recover fully from that. Batch size, the larger the batch size, the more likely you are to have these spikes. The higher the learning rate, the more likely you are to have these spikes. So there are lots of ways to deal with them. In the worst case, you might end up kind of monitoring your training run, and if you have kind of a spike that causes complete divergence and doesn't recover, you'll reset to a previous checkpoint and kind of mess with some parameters and continue from there. But again, like one of the primary things to think about here is like this train loss doesn't really tell us much. We can fit some scaling laws and try to understand how we're going to perform on downstream tasks, but doing so will really tell us how much, like, what is that difference between, say, the 1.4 billion parameter model and the 2.8 billion parameter model worthwhile for us. I alluded to this a little bit, but you can start with an off-the-shelf model, or you can start pre-training from scratch. And so here's just taking one of those curves from the previous slide, and I trained out to, looks like 18 billion tokens here, and tried to understand like what is the benefits of essentially getting a jump start on training by using an off-the-shelf model. You do see a benefit of that, right? So the transfer line here, orange, is starting from some other pre-trained model that's 1.4 billion parameters. And it does have lower loss. Again, we need to figure out like how much that loss difference makes a difference to us. But in general, this is kind of an expected finding. OpenAI has some nice literature here. I think that paper's called Scaling Laws for Transfer. But kind of the story is if you've got a very large, almost infinite set of data, if you run these curves out, they'll eventually converge. But if you don't have a lot of data, starting from some off-the-shelf model, may be beneficial. Now, if you start from some off-the-shelf model, there are trade-offs there, like you might be confined to that specific model size. And so if you want total control over model size because you have very specific concerns over latency or other factors, then you might need to train from scratch. All right, so let's talk about, now that we have our pre-trained models, we'll talk about some use cases. So this is one of the use cases I talked about in the intro. This is kind of a classification use case. So when our automated systems aren't able to handle customer issues, we hand over to a human support rep. And they'll look at these conversations, and they have basically hundreds to thousands of these template responses. And so this is a very hard retrieval problem for them. We typically depend on them to be trained up in a specific domain and know which template responses to use, because these essentially kind of denote our policy, right? So they should use their training to pick the right template response to send to the customer at a given point. And so we can treat this as a classification problem. We can recommend some number of relevant template responses. In practice, we use 5. We run the system in production. And very typical, in fact, our previous approaches here were to take like a model like BERT or any kind of encoder transformer-based model. Another typical approach these days is to take an off-the-shelf LLM and try to few-shot it to do this. But there's a couple of limitations there. So if you have been practicing in this domain, BERT encoders have basically kind of fallen out of favor. They haven't been scaled up like LLMs have. There, I think, is maybe one model that's above 1 billion parameters that's a transformer encoder, but all other ones are kind of these decoder-only LLM-style models. It's also not clear to me how you can few shots when you have thousands of classes. You kind of quickly overrun your prompt depending on the length of these classes, and you might even want multiple examples per class. And so we use a trick that kind of reduces into an LLM problem here. So we're going to treat our classes that we want to classify into as LLM tokens. So there'll be these new discrete tokens. If we have 1,000 classes, we'll create a set of 1,000 new discrete tokens. And we're just going to generate one, given the input. And we're going to mask it to just those 1,000 tokens. So this is going to help us around this hallucination problem. Hallucination basically arises because LLMs, have a set of tokens that they can, through repeated inference loops, assemble into an open set of words, right? If we mask this down just to tokens that have no linguistic meaning, and furthermore, we only generate one, we basically have reduced to a typical classification problem here. And so we're going to use that trick to our advantage here. So this allows us to benefit from the scale of these LLMs without having to deal with this hallucination problem. So I took some data from this task just for the purpose of this talk and plotted out kind of what typical results look like. So if I take an off-the-shelf model like BERT and I fine-tune it over these thousands of classes, I'll get some accuracy that looks like this, maybe right under 75%. Our team's been pre-training our own BERT models for quite a while here. We've got some previous work that we've written on like engineering blogs about this. It's useful for us. We gain about 4% accuracy when we do that. But one thing we noticed is as soon as we started looking at these off-the-shelf models, like I mentioned, like they've been scaled up compared to off-the-shelf BERT models, and they quickly start to outperform our pre-training just due to the kind of the parameter sizes of them, as well as just how much knowledge they have from their own pre-training. And so naturally, one might ask what happens if we pre-train them, like we did kind of in the preceding slides here. And at the largest model sizes, you can really start to outperform off-the-shelf models. So this is, we get basically 10% over an off-the-shelf BERT model. And this is like quite a significant impact on our business ROI. So here's kind of like a more in-depth plot of this. The bars on the previous slide were looking at kind of 0 billion tokens. So that would be kind of an off-the-shelf, LLM. And then here I'm going from 3 billion tokens all the way up to 30 billion tokens. Some of these runs I cut off early just due to, kind of increased training time. But if you look on the y-axis, this is our classification accuracy. So you see kind of an effective model size there. So the blue bar there, the blue line is, a 400 million parameter model. So that's roughly BERT-sized. Next up is 1.4 billion parameters, and up from there is 2.8 billion. So it's not quite saturated, because if you trace that green line off to the right, we know that higher accuracy is possible. So I could train another model size up from this, likely 7 billion parameters, and get at least that, if not better if we aren't at ceiling. So we're not yet saturated, but you can see like the distance between these lines as you go up on the y-axis is decreasing. There's certainly an effect of number of tokens. If you start with an off-the-shelf model, and I kind of alluded to this when we looked at our loss traces also, maybe the first 3 or 5 billion tokens are most important. And so I don't have the 0 point on here, but they drop, say maybe by 3% from the, leftmost points here. So the blue, line with 0 billion tokens would be like 75% or so. And so you see a rapid increase for just adapting a little bit, but then you see kind of this linear increase after that, which is very promising that, if you have quite a bit of data, you might be able to make trade-offs in model size to run faster models, but get higher accuracy just by feeding it more data. And so because we run this in production, we care, and for this use case, we care a lot about, say, latency and throughput. We look at plots like this to understand decisions we should be making when we go to production. So this plots throughput in requests per second against latency. And so it's very typical if you're putting a model in production to have a latency budget. So for example, if my latency budget was 100 milliseconds, I only ever want to spend 100 milliseconds on model inference. If I take the smallest model, like a 400 million parameter model, I can stay under 100 milliseconds, kind of regardless of the throughput here. My guess, if I run that out to infinity, it'll eventually saturate a GPU and go up. If I run a 1.4 billion parameter model, I can sustain kind of up to around 8 requests per second or so before I exceed my latency budget. And for a 2.8 billion parameter model, I kind of immediately exceed my latency budget. And so depending on your exact throughput and what your latency budget is, certain model sizes might not make sense. So if I need to stay under 100 milliseconds and I say have 50 requests per second, a 3 billion parameter model is just not doable. I'm gonna have to run probably 50 replicas of that to sustain that, because each one can only handle 1 request per second before going out of its budget. Moving on, I'll talk about generative use cases now. So this is our cashbot system that I talked a little bit about. Customers write in, and we have a bot that tries to help them with their problems before we hand over to a human. And so if you take a step back, the use case here is to generate some response given a partial transcript. And up until now, we've treated this as largely a classification problem. So we have a model that sits there. It's a deep learning model that classifies customer intent into one of many types of intent classes. We have hundreds of these. And then we have a rule engine that, based on that classified intent and maybe some other information in our backend systems that kind of reflect our policy, will send a mostly hard-coded response. There might be slots, like we'll fill in the customer name or something like that, but here, like, if a customer wants to reset their PIN, we've got some form text that we're going to send back that includes, here's how we'll help you, and here's an in-app link to help you do that. If they want to, say, dispute a transaction, again, we're going to have to look at some back-end systems and understand, is this transaction disputable, based on the amount, kind of the state, how old it is, things like that. And so one promise of LLMs here is that they might provide some increased flexibility. This classification system we have has a pretty high maintenance cost. Anytime we release new features on Cash App, we might need to retrain models. We might need to maintain this rule system as business policy changes. And furthermore, we've kind of covered the vast space of customer issues already. And so we're kind of into the long tail of issues here, where it really has kind of the same fixed maintenance cost of needing to retrain our models or improve the rule system, but decreasing ROI in terms of value we can provide to the business. And then furthermore, an LLM can basically customize or personalize responses based on the context. So it's going to be able to do things like copy customer names or copy customer transactions amounts. And so instead of having this mostly form text, we actually get a lot more kind of flexibility and customization around that comes for free by using a generative model. And so we're going to treat this as a fine-tuning problem. And you might immediately ask, why didn't you build a retrieval augmentation system for this? And I'm going to convince you that what we're doing is basically kind of like a poor version of retrieval. So here's kind of a hypothetical example over here at the right. You can kind of read through that. But I've mentioned this before, but we have a lot of hidden information that might need retrieved during inference. And so if a customer writes in and says, what is this transaction? Maybe they don't even specify the transaction in text here. I don't authorize that. It would not be uncommon to go and get like the most recent transaction from their accounts, or sometimes in the app we'll ask them to pick a transaction they're concerned about. And so once we have this discrete data, we can actually augment our prompt with that information. So here I've augmented it with my name, a recipient, I've made up generic music subscription company, the transaction amounts, whether it's been paid out or pending. And so these details are very relevant to a support case, and we should be using them to constrain the response that we generate here. And this is going to help us a lot around those hallucination problems I mentioned before by having this grounding in the data. And to some degree, that's what retrieval augmentation is all about, right? You pull extra information out, you put it in your prompt, and use that to ground generation. In typical systems, you might do that from embedding lookup. Here, we're doing it from just mapped data that we have in our backend systems. Another trick that we've learned here is that conditioning generation on a classification is super powerful. So I've mentioned we kind of have classifications sitting throughout our pipelines. You'll see here that I'm actually generating something that looks like JSON. And I have a classification key in there, and it says cancel subscription. And importantly, you'll note that this comes first. We know that we can train these models to be very powerful classifiers, and we can have some control over how precise they are. But a little trick that happens here is if you generate the classification label, cancel subscription, the text that follows it is very likely to be kind of related to subscription cancellation. If I generated another classification there, like dispute transaction or something like that, it's very unlikely that the text after would follow. This is kind of like almost related to chain of thought, right? Where you're kind of like inducing a space where you can generate some language that then helps you solve further parts of the problem down the line. And so we found that this like kind of conditioning based on a discrete output is super powerful. It really helps kind of, again, ground this response in information. It just so happens that this information is not in our prompt. It's information that we kind of force the model to output first. So on evaluating LLMs here. So this is what I think is probably the most important thing that people are having trouble with right now. If you've been working in ML, in NLP, it was very easy if you had a classifier to look at precision and recall and use that to make decisions about whether to launch your model and what your quality bars were. But now we have to look at response quality, and it requires quite a bit more judgment. And so I might care about things in addition to precision and recall of our classifiers, whether our response is polite, if it's biased, if it contains spelling or grammatical errors. And we have many, this is just a subset of dimensions we might care about here. We have many of these. And so once you have an evaluation rubric, these decisions on whether you use a pre-trained model, whether you do this with fine-tuning versus retrieval augmentation versus few-shotting, and any other approaches essentially become an implementation detail with trade-offs. So maybe you care about your evaluation accuracy and you use a larger model and that makes that go up, but your end-to-end latency goes down, so you have a trade-off there. Or maybe you think retrieval augmentation is the best way to solve your problem, but that induces some system complexity because now you have kind of like an embedding lookup and you're going to use that to dynamically insert information into your prompt, and that makes things more complicated. So I really think this is what people should be thinking about first when they approach LLM problems is coming up with this rubric, and then many things will follow after that. Maybe to drive that point home, we'll pull up some loss plots again. So these are plots of looking at the model sizes we've been looking at on our generation task. And kind of typical here is that you do see some model scaling. The 400 million parameter model does some level of loss here, and the larger models do better, and you get fairly quickly diminishing returns. If you have just a little bit of data there, like if you look at the far left, you'll see pretty large separation between these, but as soon as you get quite a few tokens here, those results kind of go away. We took our pre-trained models and fine-tuned them on this task, and they do quite a bit better. But I only put one line here, and that one line is, well, there's one line, there's some, kind of a shaded area representing the standard deviation. But all of the models, all the pre-trained models do equivalent here. So we know we can push loss down, but we don't really know like what that better loss corresponds to, and that's why we need that evaluation rubric. I have a theory that we're just kind of getting started with like looking at the effect of pre-training here, but my theory is that the pre-training does a very good job at the classifications we need to make throughout our pipelines. And so it's probably doing that a bit better, but in terms of the actual generated language, there's probably not a big difference in like how polite it is or whether there's spelling and grammatical errors and things like that. So we're still investigating here, but that's why I think those evaluation rubrics are quite important. And then again, this is just another one of these slides that we find very useful as we put our models in production. Because we're now generating multiple tokens, we need to care about a different measure of latency. So here we're going to care about our time per output token in milliseconds, and then we still care about throughput on the x-axis. And so as you deploy your model, you need to come out with some latency budget. For us, we know roughly how many tokens we need to generate. And so if, say, we have a budget of 10 milliseconds per token, because that helps us hit our end-to-end budget, we can run, say, a 1.4 billion parameter model, but we might not fundamentally be able to run a 3 billion parameter model for this. So we either need to increase our latency budget or come up with tricks to figure out how to bring that latency down for that model size. So wrapping up here, hopefully I've convinced everyone that we work in a closed domain in customer support. Maybe you work in a closed domain also. And once you kind of figure out what it is special about your domain and what your data looks like, you can use this to your advantage to develop specialized LLMs. You can do things like pre-train them. You can do things like fine-tune them. In our systems, we still require classification, but using LLMs is, even small ones, is kind of an attractive evolution here to what people have done before, using models like BERT or off-the-shelf LLMs. And so something that's been very helpful for our team is really everything kind of becomes an LLM. Once you do this, you can kind of simplify your model architecture, right? We can rally around these decoder-only architectures instead of encoder architectures. We have a very consistent training objective here, and so we can kind of standardize around very specific tools for pre-training and fine-tuning. And it simplifies kind of all aspects of that pipeline. Model servers are still a bit of a moving target there in terms of how you deploy these types of models, but I'm hopeful that we can standardize around that too. So that's it. I'll take any questions now.